Hello and welcome. Here we shall start with learning some Bengali. Pretend that you have no idea about the Bengali alphabet and you have just collected a few samples of Bengali letters from various newspapers and billboards, etc., and made some careful sketches of these letters, the letters that you see around my head. Your hope is to be able to recognize future instances of these letters. Now, we can see that certain letters look similar to certain other letters, so our plan is to group similar looking letters into a single set. Now, of course, the question is there might be some minor variations from one letter to another letter, or one letter to the same letter in a different font, so we have to ignore minor variations. The question is, what is meant by minor variation? How much variation can be considered minor? That is the important question. Now here is one possible attempt to do this grouping. What we have done just now in this example is called unsupervised classification or clustering. A more efficient, a more effective way of learning the alphabet would be to do what is called supervised classification. For that, you will need a supervisor, a teacher, that is a person with some kindness in his heart and some knowledge about the Bengali alphabet in his head. Such a person would kindly tell you the true identities of the different letters that you have collected. Then you will have a much better chance of identifying any future instance of any of these letters. What we have done here, that is supervised classification, is basically how we learn an alphabet in our childhood. Now this technique is useful for many other purposes in statistics as well. Statistics generally works with tabular data. We might think of our data set as a table, like this. Here, each row of the table consists of two types of information. First, what we see, the picture. And then, what the teacher told us, the true class of each letter. The true identity, the true class of each letter. Now, of course, for the future data set, that is the new letter that you are trying to recognize, there we only have the picture and not the diagnosis of the teacher, so we have put a question mark in its place. Now you can think of the entire setup as examples followed by exercises. So it is something like classroom teaching. The examples have Each of the examples have a problem statement followed by a solution worked out for you by the teacher. The exercises that follow are very similar. They also have a problem statement, but the solution has not been done for you. You have to do the solutions. Similarly, you have to recognize those future letters. Now in statistics, the general setup will be like this, a table. In the table, there are two parts. The first part, the so-called training data set, is the thing that plays the role of examples. Here you have your measurements, the things that you see, and the true class, the thing that the teacher tells you. That is the training set. This is followed by the test set, where you only have the measurements, but not the true classes. Those are the things that you have to guess. This is the general setup of supervised classification. Supervised classification is used in many practical problems. Take, for example, the problem of credit risk or the problem of loan risk determination. A new customer comes to a bank asking for loan, and the bank has to guess whether this loan is going to be repaid properly. For this, the bank has already collected lots of relevant information about its past customers, the past loan cases, and for those past cases, the bank of course knows whether the loans were repaid properly or not. This thing, whether repaid properly or not, whether good loan or bad loan, that serves the role of the true classes. There are two classes here, good loan and bad loan. Now for the new customer, they can again make all these measurements, they can collect all these relevant data about the new customer. Based on that, they have to guess what is going to be the class of this loan case, whether this loan is going to be a good loan or a bad loan. So that is an example of supervised classification in the banking sector. Now here is another example of supervised classification for medical studies. When a doctor learns medicine, he or she basically learns to diagnose a disease based on past data. So for lots of different past cases, different diagnostic measurements are known, and it is also known whether this particular patient had the disease or did not have the disease. Now when a future patient comes, the doctor quickly makes similar diagnostic measurements, and comparing these to the past database, he or she can quickly determine, or at least can guess, whether this particular patient has the disease or not. In statistics and machine learning, there are various techniques available to perform supervised classification. In this lecture, we shall take a look at one of them, called the classification and regression tree, or CART for short. This technique, as its name suggests, uses a tree. No, not a real tree, but a diagram like this. It is something like a real tree turned upside down. The junctions and the tips are called nodes. The topmost node is called the root, and the bottommost node that has no branches hanging from them are called the leaves. Now CART proceeds in two steps. The first step, which we shall call the grow step, uses the training data set, that is the examples part of the data set, the part for which you have the true classes given to you. It uses that training set to construct a tree. Then in the next step, the predict step, we take this tree and also the test part of the data set, the test set, that is the exercises thing for which you have only the measurements and not the true classes given to you. You take these two things, the tree constructed from the build step and this test data, and using these two things you construct your appropriate guesses for the true classes. So these are the two major steps of CART. Before delving deeper into the working of CART, let's take a simple overview of the two parts, grow and predict. For this, we shall employ a simple toy two-dimensional example. I call it two-dimensional because we have two measurements per cases, x and y, other than the true class of that case. So we can show this visually using a scatter plot. X and y will determine the position of each point in the scatter plot, and the true class will be coded by color. So in our example, we have three classes. So we have got three colors and two variables, x and y, two measurements. Now the way CART proceeds is like this. It will split the data space using what is called an axial split, that is a line, a straight line which is either horizontal or vertical, parallel to the axis. So the first cut that we make in our example will be a vertical cut, like this. Now notice that because of this cut, because of this split, the entire space is now partitioned into two halves. In the first half, we have only red points. So all the points in the left half are of the same color. So there is no need to split that half further. Now let's look at the right hand half, which is not pure. So we have to further split that. We can either choose a horizontal split or a vertical split. A vertical split means based on the x variable. In this case, we split at the point A, x less than A or x greater than A. We could include the equality case either in the left half or in the right half arbitrarily. Now again, we can either choose a vertical cut or a horizontal cut. Let's take a horizontal cut in this case. Again, we have got two halves. So these are the halves or two parts, not necessarily equal, two parts of the right part from the first plate. So we are partitioning it recursively. Here again, the top half is completely pure. All the points there are of the same color. We need to split the lower part further. I can again choose a vertical split or a horizontal split. Remember, a vertical split means based on the x variable, a horizontal split means based on the y variable. And also notice, as we make each split, the tree is growing. Each split causes one leaf node to branch out into two leaf nodes. And every non-leaf node is labeled with an inequality. Something like x less than a, y less than b, something like that, involving only a single variable and a single cutoff point. Whenever that condition is satisfied, so you can think of that inequality as if it is like a question. If that is satisfied, if the answer is yes, then you follow the left branch. If the answer is no, if that inequality is not satisfied, then you follow the right branch. So now we are trying to split this lower half. Well, let us take a split based on the y variable again, that is a horizontal cut, and we get something like this. And we can see that all the partitions are now pure. In every rectangle, we have dots of only one color, so no further cuts are warranted. We stop this process and we label each of the leaf nodes with a color. The color of the dots in the corresponding rectangle. Well, that was the build step of the card. Now we shall take a look at the predict step of card using the same toy example. In this step, we want to solve some exercises. We will bring in some test data. Some case for which we have the x and y values but not the true class. So here is one example. From the scatter plot itself, we know that it must be in the blue class. But of course, here we could draw the scatter plot because we have only two variables. Had there been more than three variables, we would not be able to use a scatter plot. So let us see how we can use the tree generated by the build step as an alternative that may be used for all dimensions. We start with the root node and ask the question that labels the root node, namely, is x less than a? For our case, the answer is no. So we take the right branch. That takes us to the question, is y less than b? The answer now is yes. So we take the left branch. That leads us to the next question, is y less than c? Here the answer for our case is no. So we come to a leaf node labeled with the blue color. That is, we conclude that this new case must be a blue case. Now that we have an idea about the overall working of card, it's time to take a closer look at the tree building process. As we have already seen, the tree building proceeds step by step by choosing an appropriate split at each step. The split is always an axial split, that is, it always uses a single variable and a single cutoff. The question is which variable to use and which cutoff value to use. Now obviously we want to choose a split that is the best. What is meant by best? To quantify that, we need some measure of goodness of a split. There are quite a few criteria to quantify this idea of goodness of a split, we are going to discuss one of them. Consider this particular rectangle of points and consider this cut A as opposed to this cut B. Which one do you think intuitively is a better cut? Of course, cut A, because it separates the color well. On either side we have pure subrectangles, but in case of cut B, the two colors are mixed on either side. So this color separation, how well a split separates the colors, that could be one way of measuring the goodness. In order to quantify this, we shall use the concept of misclassification. We shall explain the idea of misclassification using a tricolor example. Consider this particular cut. Here you can see that to its left, most of the points are red. So the majority is red to its left. So if we want to label that entire left half with a single color, the natural choice will be red. In that case, the minorities, green and blue, will be misclassified as red. So the total number of misclassifications that we shall get will be 1 plus 2, that is 3. If I look at the right hand half, there the majority color is green, so the natural choice of label will be green. So the red and blue points will be misclassified. So there you have 4 more misclassifications. Thus, this particular split gives rise to 3 plus 4, that is 7 misclassifications. This number 7 may be used as a measure of how bad this particular split is. With every possible split, we can associate one such badness number, and then cut picks the cut with the least amount of badness. This process continues until we have a rectangle which is pure, all the dots are of the same color, or when the amount of misclassification is below a certain pre-specified threshold. So that's how cut works. It is simple, fast, and since every split uses only a single variable, so the generated tree is quite easily explained even to a layman. It's nice, but in certain cases, card does not perform so well. Card at every step will make only axial cuts, that is, cuts that are parallel to one of the coordinate axes. It may happen in certain situations that you need an oblique cut like this, but card cannot make such cuts. Here is an example. Here we have 3 different classes. They are quite well separated, but the best separating lines unfortunately are oblique. Since card cannot make such oblique cuts, it will try to approximate these by using a large number of axial cuts, and as a result, the tree produced by card will be much larger than what is really needed. You could have done the same classification using a much smaller tree only if you allowed oblique cuts. But since card does not allow that, it will give you an unwieldy large tree. In order to prevent card from generating huge trees, we have to keep some check on it. And that is done using what is called a cost complexity parameter, typically denoted by the letter alpha. This is like the price that you have to pay in order to introduce a cut. So every cut comes with a price tag. You have to pay an amount alpha in order to do that cut. So the larger is the tree, which means the greater is the number of cuts that you have made, the greater is the cost. So now what cart will actually try to do is not merely minimize the number of misclassifications, but it will try to minimize number of misclassification plus alpha times the size of the tree. The size of the tree means the number of nodes in it. Thus, because of this alpha times size of the tree term, larger trees are penalized. You will naturally be unwilling to go into large trees because then that quantity will go up. So this alpha controls something like the trade-off. How willing are you to grow the tree for a certain reduction in the number of misclassifications? So the entire cart algorithm proceeds like this. It will first grow a huge tree and then it will prune it back to some extent, that is, look for a sub-tree which will minimize this misclassification plus alpha times size of the tree. And that minimizing sub-tree will be the final output of the build step of cart. Well, basically that's all the theory that we wanted to discuss about cart in this lecture. Now we shall take a look at how to implement cart using R. Now we are going to see how to carry out cart using the R software. We first start by firing up R. Now we need to load a library called rpart, library rpart. It is always installed by default. You do not have to install it. The moment you install R, it gets installed automatically, but you have to load it in a session where you plan to use rpart. And that introduces a function rpart. Rpart stands for recursive partitioning. So let's quickly look at the help, and you can see lots of help which you should read at your leisure. Now for the time being, let us see what is the data set that we plan to use. We shall use the famous iris data set. So these are the variables that are present in the iris data set. If you do not know, it consists of 150 flowers. For each of them, you have measurements on 4 variables: sepal length, sepal width, petal length, petal width, and the species of the flowers. All the flowers are of type iris. There are the 3 species. So if I just take a look at levels, iris, the last column. So these are the different levels: iris setosa, iris versicolor, and iris virginica. And we want to identify the different flowers, the species of different flowers based on these 4 measurements. So let's quickly carry out our part technique. So I use some variable names, a fit r part, and you are trying to predict species, that's your dependent variable, on all the other variables. So you could just write tilde dot name of the data set and hit enter. So you get whatever you wanted to get. Let's take a look at how the fit looks like. Plot fit, and you get a tree like this. Now this tree by default is not annotated, so you do not understand anything, what the leaf nodes are labeled with, what are the inequalities. So for that we will need to add texts. So write text fit, and then look again at the generated plot. Now you see that we have labels. So the first node, the root node, says petal length less than 2.45. If so, you go down the left branch and you classify that flower as setosa. Oops, you see setosa is not completely printed. Part of it is chopped out. And that is because the name is too large and it has become covered by the margin. Same thing is happening here. So you can change this using the plot command itself. When you write plot, you set margin equal to say 0.1. So margin equal to 0.1 will allow that much extra margin so that you can fit your text into it. So let's quickly see. So it has now allowed some additional margin so you can completely read setosa and virginica. that amount 0.1 is something that you have to set by trial and error. Okay, so now we have a pretty simple tree. You just look at petal length. If petal length is pretty short, immediately you say that that is setosa. And if petal length is somewhat larger, then you look at petal width. If the petal width is less than 1.75, that is versicolor, otherwise it is virginica. Pretty simple stuff. So let's see whether this classification rule is really doing a good job or not. So I want to predict. So how do I predict it? I will call it pred. That's a new variable. Predict. And the variable name was fit. And I want to predict the classes. Type equals class. And that gives me the predicted classes of all the 150 things. For example, here I see virginica. 122nd entry, 122nd entry is virginica. That means the 122nd entry has been predicted to be in class virginica. Now let us see whether this is really correct or not. A little cross tabulation would help. Table, and I just now stored it in pred, that is the things predicted by card. Now I know what the true things are. Iris, the fifth column of iris. So this is what I know to be the true thing. And this is what I have predicted using card. So I make a cross tabulation. Here are the predicted things and here are the true things. I see 50 out of 50. All the setosa have been correctly classified. Versicolor, no, 49 have been correctly classified as versicolor. 1 has been misclassified as virginica. For virginica, the situation is slightly worse. 45 has been correctly classified as virginica. 5 have been misclassified as versicolor. So that is basically what you get. Now we also talked about that cost complexity parameter. You can very quickly see how that is incorporated in the output. You go to fit dollar CP table, that is the cost parameter or complexity parameter table, and that will give you certain values. So it says that if the value is 0.5, if alpha is 0.5 or more, then the number of split will be 0. That is, it will be the wisest thing is not to split at all, because cuts are so very expensive that it's a good idea not to cut at all. So split is just 0. If you lower the price of a cut from 0.5 to something above 0.44, then the cart algorithm will say, okay, one split is what we should do. In that case, the amount of error will be 0.5. And if you allow even cheaper splits, if the price goes down, if alpha goes down from 0.44 towards 0.01, then you will have 2 splits. That's the thing that we saw. And even if you make it cheaper, you do not need to go any further because the error has come down very low already. So that is basically the idea. Okay.